Hey, good evening, everybody. This is TJ from Friends of Ottawa National Wildlife Refuge. We're just giving everybody maybe another minute to join. I have a couple of other attendees. All right. It's 7 o'clock. Good evening, everybody, for joining. My name is TJ. I'm one of the board members for Friends of Ottawa National Wildlife Refuge. Today, one of our rangers at the Ottawa National Wildlife Refuge, Basia Gawin, she would be presenting science, math, and art around the snowflakes. She then also will show us how to make a paper snowflake at our home. So, Basia, thank you so much for taking the time. Uh, you know, um, I will turn it over to you. Are you already sharing your screen? So maybe we can get started. So what we'll do your presentation first. I know with you have three sections for science, math, and art. There'll be a pause between each of those sections, and we can take Q&A, any questions that come in, and I'll monitor the chat so we can take those questions there. But thank you
Awesome.
again for doing this. Yeah.
Thank you, TJ.
Over to you. Yeah, over to you.
So welcome, everybody. This is Snowflakes, Science and Art. Like TJ said, my name is Basia. A lot of people know me as Ranger B. I've been at Ottawa for about a year and a half, and I am funded through the Great Lakes Restoration Initiative. So everything that I do, I try to tie back to the Great Lakes and specifically Lake Erie. And where do snowflakes come from but water? So I'm excited to share some of the things that I've learned. When I first started working on this presentation, I thought snowflakes, they're so pretty, they're so fun. And then it turned out that snowflakes are actually a lot of math. So hopefully we can focus more on the fun part and not so much the math part, but I want to give you a good overview of what a snowflake is, how it forms, and then different ways that we can see it as art and turn it into art. But my first slide, we're going to start with a quick little video. So I just want you to observe and see what you notice. This is a video of a snowflake growing under laboratory conditions. And there's a lot of good images of snowflakes that have been grown in the lab. So these have very doctored lighting, but you can see the incredible variety in shapes and sizes of all of these snowflakes.
Fascinating, yeah, well.
They are just stunning. I could look at these pictures all day. So I wanted to start with one quote from Henry David Thoreau, which most of you should be familiar with, so I'll give you a minute to read that. I really love the line that says, "I should hardly admire more if real stars fell and lodged on my coat." So people have been observing snowflakes for a very, very long time, and people like Henry David Thoreau made constant observations, recurring observations. He references the 13th of December. So, he was observing these snowflakes many, many times. But throughout history, most people that were looking at snowflakes noticed pretty quickly that they were six-sided star shapes. So there's Chinese documents from the 2nd century BC that reference that six-sided shape. There's some philosophers that reference those star-shaped forms. Kepler, who we probably know from discovering that planets move in ellipses, he wrote a book called The Six-Cornered Snowflake in 1611. And he also was wondering why it's a six-sided shape. And trying to figure out, like, if liquid water moves around, why does solid water make this shape? And he had this theory that there's an agent in the orderly stacking of what he called globules that represents the smallest natural unit of a liquid like water. So he thought if you go down to the microscopic level, there's something that is that shape. And as it grows, as it gets bigger and we can see it, it retains that shape because that's kind of how it's stacking. And then Descartes also drew some six-folded stars and what he called ice flowers in his meteorology book in 1637. And Hooke started looking at a microscopic level and describing the branching patterns in his writings as well. There's a pretty well-known book called Snowflakes, a chapter from the Book of Nature by Israel Perkins Warren from 1863. And these people back then were a lot of times observing snowflakes just with the naked eye. They didn't have photography equipment, so they were sketching what they could. But the snowflakes melt pretty quickly, so they would try to catch them on dark fabric and then sketch them out before they melted. Over time, magnifiers were invented, got better, and so they got a better look at these snowflakes. But his book has a lot of different descriptions, drawings, scientific explanations and theories, but also religious declarations and just poetry about the magnificence of winter. So he was also very into observing snowflakes, and this is what sketches back then of snowflakes looked like. So also those six-sided shapes and in all varieties. One of the snowflakes experts, someone who's pretty well known, is Wilson Bentley. He wrote the book Snow Crystals. A lot of times people call him Wilson Snowflake Bentley. And he was born in Vermont in 1865. And his mother said that he was always interested in tiny things in nature. He was always out there looking for the smallest things to observe. And so she ended up giving him a microscope for his 15th birthday. And that grew into even more of a passion. And he ended up getting a camera in 1885, and he was the first person to photograph a snowflake. There was a lot of trial and error in that, but on the 15th of January of 1885, he took his camera and microscope out in a snowstorm and ended up taking this picture, which back then you didn't just snap a picture and have it on your phone. He had to have a 1.5-minute long exposure. But when he finally saw the developed image, he said it was the greatest moment of my life. And that kept blossoming. He kept taking pictures of snowflakes. He wasn't finding any two that looked alike. And so he tried to take pictures of as many as he could. And he ended up having about 400 pictures before somebody from academia noticed that he was working on this project. He just assumed that this was a really interesting topic and that a lot of people were photographing snowflakes. Turns out that he was the only one doing it. And so George Perkins from the University of Vermont learned about his project and convinced him that it was a really important project and convinced him to write a book about it. And he ended up publishing a book with a huge collection of snowflake photographs. There were about 2,500 pictures included in that book. And now there's other books about him. So there's a children's book called Snowflake Bentley that you can check out and read, but a very well-known figure in the history of studying snowflakes. And here are some pictures of snowflakes that he took. So a little bit different than the pictures we saw at the beginning, but these were the first pictures of snowflakes ever. Now, as we're talking about snowflakes, I think it's important to distinguish between snowflakes and snow crystals. So technically, the pictures that we were looking at were snow crystals. Each individual one is a snow crystal. When you get them together in a group, that's what you would call a snowflake. But in common language, those two are interchangeable. So even though I will be describing snow crystals, I'll keep referring to them as snowflakes. As people have described for a long, long time, they are always six-sided and have six-fold symmetry. So going back to Kepler's book and him theorizing that those tiny units were being packed, that turned out to be true with those tiny units being atoms. They just didn't know about all of that back then. And his theory wasn't proved until 1998 using computers, and it wasn't published till 2005. So he was on the right track a long time ago, just didn't have the technology to actually prove it. So today we know that the snowflake reflects the internal order of water molecules as they arrange themselves in the solid state. And I'll have some diagrams in a little bit. But molecules tend to be pretty lazy. They will settle in the lowest energy state. So usually that involves some form of symmetry, but they don't want to be working if they don't have to. And no two snowflakes are alike. That was a very common observation. That's something that we still hear today. And we'll talk a little bit about why that is as well. But as I was doing this research, I came across an article in American Scientist that said that understanding snowflake formation requires a rich synthesis of molecular dynamics, surface physics, growth instabilities, pattern formation, and statistical mechanics. And I am more on Kepler's level than I am on a huge scientist level. So we're going to cover kind of the basics here, but we can always get deeper into these things. And if something's over your head, that's okay. A lot of this stuff was also over my head as I was doing this research. So as we get closer to modern day, people started using X-ray diffraction to study snowflakes. That led to crystallography and to more kind of hard sciences. As the semiconductor industry kind of grew, a lot of these materials, modeling things, growing crystals became more like economically something that people were interested in. And a lot of that has been applied to studying snowflakes. Back in the 1930s, there was a physicist in Japan that started not only observing snowflakes in a lab setting, but started growing them. And he figured out that temperature and humidity are kind of the two big factors that control what happens with a snowflake. Today, the modern expert would be a professor at Caltech named Kenneth Libert. And he has a lab group dedicated to studying snowflakes. And the lab group studies the physics of crystal growth and pattern formation in ice. And there in white there is basically what his lab studies, but there's a lot of big words in there. And also there's some people working parallel to him, but they're looking at more the math side. So those last two names on there are professors at the University of Wisconsin-Madison and University of California, San Diego, who are working on computer modeling of snowflake growth. And this is just a picture of how they grow a snowflake in the lab. So they'll have a pin or a very thin element, kind of put a starter on there. So droplet of water, a piece of dust, something that will attract the water droplets. And over time, they can grow that crystal. And they can actually grow what they call designer snowflakes. So if you go on his website, he has a lot of good explanations on there. He has a lot of pictures like the ones I showed at the beginning. So snowflakes also involve some math because they involve symmetry. There's a pretty simple diagram of 3 types of symmetry that we can observe just out in nature. Bilateral symmetry is where you can draw one line through something and it has a mirror image on the other side. If we were to divide that fly in half the other way, so instead of drawing a vertical line, we drew a horizontal line, that would not be a mirror image. And so there's just one line of symmetry, bilateral symmetry, that is going to be very helpful for the art part of snowflakes. So definitely remember that one. Then there's radial symmetry, where you can draw multiple lines through it, and those will intersect in a center point. Basically, you can rotate the object and it'll look the same no matter how it's rotated. So that will be what a snowflake has as well. Then there's spherical symmetry, which at this point we have to think in 3D. So think like a ball where you can not only rotate it, but also spin it on the other axis and it'll look the same. So that one we are not going to be covering today. But if you look at a snowflake, because it's 6-sided and has 6-sided symmetry, you can do those rotations and it looks like 6 of the same exact picture. And then it also has those reflections or that bilateral symmetry or radial symmetry where you could draw those lines bisecting it and it looks like a reflection of itself on the other side. And then something else interesting in math that I came across that doesn't relate much to snowflakes, but shares a name, and I'll explain that in a little bit, are fractals. Fractals are patterns that repeat forever, and they are self-similar across different scales. So one that people are pretty familiar with, and one of the most basic ones, is this triangle, where you start with a big triangle. Inside that, you would draw a smaller triangle, and then inside that, you would draw an even smaller triangle, and you repeat this forever. And no matter how far you zoom in, it's going to look the exact same. So this is a very basic fractal, but there's also very complex ones like the one on the right there. And the reason I decided to bring in fractals was because there's something called a Koch snowflake. Started out as a Koch curve, which you see at the bottom of that slide there. And it was published in 1904, one of the first fractals that was described. And what you start with is an equilateral triangle, and each step you add 2 more triangles to that equilateral triangle. And I have a little video that will show that as well. And so that was originally described by a Swedish mathematician, and then later on, an American mathematician adapted that into a snowflake shape. So he took a few of these Koch curves and put them all together. And then as I kept researching this, stuff like this started popping up, and I said, I'm done here, so we will be done here. But here is an example of that Koch snowflake. You can see it starts out as a triangle, then that triangle is divided up into smaller triangles, and it kind of keeps growing. And something cool about this is that it encloses a finite area. So the area inside is going to stay enclosed, but the perimeter is infinite. You can keep adding more and more to the perimeter, and it keeps growing forever. And this is an illustration of that self-similar across all scales. So we start out big, and no matter how long we zoom in, we're going to have that same pattern repeating over and over. And a cool application of fractals is that people have actually used them in animating movies. So as movies have moved towards computer animation, you can use fractals as a basis to illustrate geography and mountains and things like that. So next time you're watching a movie, you can think about math and fractals. I'm going to
That's
take
really
a pause
awesome.
here.
Yeah.
Any questions so far?
Yeah, feel free to unmute yourself. If you have a question, you can put it in the chat also. But fascinating stuff, Basia. I don't see anybody, but you know what you has
Nothing
covered so
yet.
far, it's eye-opening. Yeah.
Should we force them to participate now?
Yeah, maybe let's do that, yes.
Okay, so we'll leave the math behind, but we're gonna go to science. So a snowflake made out of water. Everybody knows that water is H2O, 2 hydrogen atoms, 1 oxygen atom. And I work a lot with kids in my job, so we talk about the water cycle a lot. So water can change phases, solid, liquid, gas. Snowflakes obviously are in that solid phase, but in order to get snowflakes, we have to go through the water cycle. Lake Erie isn't a big snowflake, it's liquid water. So how do we get there? So if we have solid water or ice and it turns into a liquid, what is that process called? Somebody brave, unmute yourself. Or put it in the chat.
Yeah. You showed me, so maybe I'll type, it's melting.
Melting.
Yeah.
Perfect. And then if we have liquid to a gas, so from a liquid to a gas, that would be evaporation. From a gas to a liquid, so the opposite of that, condensation. So think about if you've got like a glass cold beverage outside on a summer day, a lot of times it'll get wet on the outside. That's just because water is condensing onto that glass. Liquid to a solid is freezing. So that's what's been happening a lot. Good job, Lori. You got it. Liquid to solid freezing. We're getting rain that's freezing into ice. And then solid to gas. This one's a little bit trickier. I love teaching the 5th graders this word if they don't already know it. Sublimation. There's your new vocab word. Yay, Paul got it.
Paul got it. Yeah.
So sublimation, you go from a solid to a gas. So if ice turns into a gas, into that vapor, a lot of times people think about this with dry ice. You can actually see that in action, but water can do that as well. And then last one, gas to solid. This is going to be our key one for snowflakes.
Gas to solid.
Crystallization. Deposition's a good guess though, yep. So all of this is happening in the water cycle. Water is moving throughout the planet. And usually this happens at known temperatures and pressures. It's pretty common knowledge that at 0 degrees Celsius, water freezes. At 100 degrees Celsius, it boils. And that's what that scale is based off of. But there's some funky things that can happen if you start playing with pressure, if you start playing with temperature, if you start playing with humidity. And so if you've never heard of super cooled water, you can actually get liquid water to go below freezing and not freeze. So it's a cool science experiment. You can look it up on YouTube or somewhere else and try it yourself at home. Takes about 2 hours in the freezer, and then you can take out super cooled water and make it freeze instantly. So as we're talking about the water cycle, there's a lot of the water cycling happening throughout the planet, and there's a lot of weather patterns, a lot of wind patterns that will impact where we get snow. So this picture illustrates the global atmospheric circulation, basically how air moves on a planetary scale. It explains how heat gets moved around the planet and how storm systems move. There's a Hadley cell, Ferrel cell, and polar cell in each atmosphere. And there's bands of low and high pressure across the planet. So those low pressure bands, usually at the equator, and then you get some high pressure bands, and that all has to do with the circulation. And usually you get hot and dry weather when there's high pressure. So if you see that high pressure on the north of Africa, that's where you would get like a desert. And then you get stormy and rainy weather where there's low pressure. And so like the equator is known for being very rainy, very wet. So these cells are kind of impacting the globe on that big scale. But then we get down to a smaller scale and we get what are called fronts. So if you ever watch the weather, this is what they're talking about when they're talking about cold fronts and warm fronts. There's also stationary fronts and occluded fronts. So this gets a little bit more complicated. But basically what happens is when masses of air run into each other, they have to react to each other. And what happens is that warm air rises and cool air sinks. So in order to form snow crystals, a mass of warm, moist air, so it has a lot of humidity in it, collides with another mass of air, and that forms that weather front. So two very different air masses. That warm air is pushed up and it cools as it rises, and that causes the water that's in that high water content air to condense, and that can condense on on particles of dust, on other droplets of water, and that's what forms clouds. So that warm air rises, it's very wet, it forms those clouds as it cools, and it can remain in that super cooled state. So if you go back to that science experiment, it's below freezing, but it's still liquid, or it can freeze, and that freezing process kind of escalates on itself, and it can grow either bigger rain droplets, or if it's really cold, it can grow snow crystals or sometimes hail. And so these warm and cold fronts, if you're watching the Weather Channel, look something like this. That blue line would be that cold front, the arrows point the direction it's headed. That red line is going to be the warm front. Also, the shapes are on this direction that it's headed. And so we're in a place in Ohio that gets some snow every year. Usually, these are averages on this map. So if you go closer to the equator, farther south, you get a lot less snow. So a lot of Florida, Texas will have an average annual snowfall of 0 inches. We know that's not true every year. Like this year, they got snow. But if you take data on this over a long period of time, these are the averages that you get. So looking up towards the Great Lakes, you're getting up to or over a foot of snow in some places. But then in addition to all the other weather patterns we've talked about, you can get like El Nino and La Nina years in which stuff is shifting differently. So these averages aren't going to be true for every single year. So down to some more microscopic science, I guess. We'll go back to the fact that a water molecule is 2 hydrogens, 1 oxygen, and it's actually in the shape of a tetrahedron. So if we had a microscope that could zoom all the way down to that atomic level, that molecular level, we would see this tetrahedron shape. It's kind of a pyramid with a triangular base. And in the center there is the oxygen, and it has only 2 hydrogens. So 2 of those white things are there, 2 of them are not there, which means that there are 2 lone electron pairs. They're negatively charged and they'll repel each other. So the hydrogen side is going to be slightly positive. So here is that tetrahedron with the 2 hydrogens, the 1 oxygen, those lone electrons. They are going to be slightly negative because electrons have that negative charge, and those hydrogens are going to be slightly positive. So if you put the charges on there, it's going to look a little bit like this. And people have managed to study this down to just the smallest level, and they've even figured out that the angle between the 2 hydrogen atoms is consistently 104.5 degrees. So just how those electrons repel stuff and the shape of this tetrahedron, that's what a water molecule looks like. We talked about water being in those different states of matter, but when you have states of matter, this is an illustration of what those molecules are doing. So in a gas phase, they would be spread out, they're moving around a lot. In a liquid phase, they get closer together, they lose energy, so they're not moving as much. They'll kind of sit in a clump, but they're still moving past each other. And then once you get into a solid, they start stacking and ordering themselves in that lowest energy state. So with water molecules, it looks something like this. On the left is going to be a liquid where they're all kind of sliding past each other, still moving around. And on the right will be that solid phase where they start packing into that pattern. And you can see they start arranging themselves. And so this is a different view of that. And you've got little hexagons forming, or something that people call a honeycomb pattern. And this is what happens with water under normal atmospheric pressure and a temperature just below freezing. So once you get below that 0 degrees Celsius, it will start forming these hexagons. This is a really cool pattern that you can see out in nature. If you look like at a beehive, they also build that in hexagons, and it's just a very efficient way to pack things. So everything will have one of these phase diagrams. This is the one for water, which is what we're talking about. And you can see that you can play with temperature and pressure. So like we've been talking about, water boils at 100 degrees, freezes at 0 degrees Celsius. And there's places like the triple point where it can exist in all 3 phases at once. So it can be a solid, liquid, and gas at a certain temperature and pressure. But once you start changing temperature or pressure, it will move into one state over the other. And usually, if we're on the surface of the Earth, we will be at that same pressure. But sometimes, if you're like climbing a mountain, you might experience different pressure. Or if you go fly on a plane, they'll pressurize the cabin because there's lower pressure up there. And so if you were to try to boil a pot of water on the top of a mountain, it doesn't have as much pressure pushing down on it as it does at atmospheric level. And so it will boil at a lower temperature than it will at sea level. Sometimes if you're buying like those prepackaged bake mixes, you might see at higher elevation change the temperature or make this change. And that's just because of the differing pressure. So there's some cool things that you can do if you're able to adjust either temperature or pressure or humidity. So this is a different diagram where you have temperature on that x-axis again, but on the y-axis, instead of that pressure, we have humidity. So how much water is in the air. And you can have different snowflakes or snow crystals form depending on how you play with that temperature and humidity. So this is what that scientist from the University of Japan was working on in the 1920s and 30s. And he discovered that if he varies these factors, he can grow different types of snowflakes. And on the right there is a picture of that basic hexagon packing pattern. So as those molecules start packing together into those hexagon shapes, you start getting a bigger and bigger hexagon shape. So what Kepler was talking about long ago. And that hexagon shape will have a basal facet and a prism facet. And there's times when water molecules will prefer to latch on to the prism facet, so kind of the sides on that diagram, and there's times when they will prefer to latch on to that basal facet, so the top and the bottom. And those different conditions can cause different shapes to grow. So if you look to the left of the diagram, you'll see needles. Those form when those water molecules are preferentially attaching to the top and bottom, so those basal facets, and over time it'll grow into this very tall hexagon. Versus if you go to colder temperature, lower humidity, you'll start seeing plates, and in that case, it's attaching to the sides or those prism facets more so than the basal facets, so it'll start growing wide instead of tall. And so all snowflakes start out as this little hexagon shape, but then they experience something called the Mullen-Sakirka instability. And so if you're looking at that prism picture on the right, you can see that all of the 6 points of that hexagon stick out a little bit farther than the sides. And as that crystal is growing and starts growing faster, those are kind of like reaching out farther into the humidity, and they're picking up those water molecules that are around. And as you can imagine, when one of those corners picks up a water molecule, it gets even farther away from the sides than it was before. And so it has a better chance of reaching more water molecules. And it turns into a positive feedback loop. And that's why you get that six-sided shape of the snowflake, because those corners are basically sticking out farther and collecting more of those water molecules onto that snowflake. But you can play around with temperature and humidity and make different shapes. But the snowflake will grow to be symmetrical because it's so tiny that all of it is experiencing the same temperature and humidity at the same time. Now, a snowflake 2 feet down in the cloud is going to have slightly different temperature and humidity. It's going to be floating around a little bit differently. But that one snowflake is so small that the whole area of it experiences the same conditions, and so it's going to grow into that symmetrical star shape. And something cool that I found when I was looking at this diagram and researching it a little bit, those needles can also form when you have solid ice and it starts melting. A lot of times there will be dust or other impurities in between the water molecules, and so they'll hold on to each other really tight, but they'll start melting in between each other. And there's some pretty cool videos out there of what people call candle ice, where it's just needles and needles on a lake. So that's another thing you can look up, those candle ice videos. But as I kept looking into more information about this diagram, there were even more big terms like structure-dependent attachment kinetics, and knife edge instability, which is a hypothesis. And I was like, I think we know enough about snowflakes for now. So any questions about any of the science stuff that we've covered so far before we move on to art, the fun part? I'll give folks a minute if they want to put it in the chat. All right, well then let's move on.
I just had one. So like this prism and the basal facet that you were talking about. So let's say if they connect to the prism side, that means then the shape is of a hexagon, right? Versus being a needle.
So the needles are just very, very tall hexagons.
Okay.
Whereas the plates, you've got thin plates, solid plates, or just plates. Those are going to be still in that hexagon pattern, but they're going to be very long. So they're going to be built of hexagons, but more of a sheet.
Okay.
The needles are just very tall hexagons altogether.
And they will be attached to the prism side of that facet. Okay.
Prism side will be the plates, basal sides will be the needles.
Needles, okay.
So there's water molecules attaching to both sides, but sometimes they prefer one over the other. So if it was just a group of molecules, we wouldn't be able to see the needle.
Okay.
But if there's kind of a few hexagons together, that's when we'll start seeing it with the naked eye.
Makes sense.
And another thing I didn't mention with the snowflake versus snow crystal, snowflakes are made out of water, so they're actually translucent. They're clear, but because they start gathering together, you start seeing them as white. So something that blew someone's mind when I was doing this program in person last week was that polar bears also have clear fur. They don't have white fur, but it's hollow on the inside, and so it actually reflects the light as it hits it, and that's why polar bears look white, even though they have clear fur. So kind of a similar thing with the snowflake. They're clear, but once you start getting more, they start reflecting the light, and they start looking white. All right, so moving on to art. Paper cutting, which is what I've been doing with snowflakes, has evolved all over the world in different cultures. But if we really want to trace it back to the beginning, there was someone in China who invented paper in 105 AD. And then paper cutting as a craft started appearing in about the 4th century also in China. And there's actually a surviving paper cutout from the 6th century, which is incredible. Because if you think of, like, sometimes we find paper trash outside, and after just a few days, a few weeks, it's looking pretty worn. So it's awesome that there's something from the 6th century that survived. But in China, they started associating paper cutting with health, prosperity, or decorative purposes. A lot of times they would be using the color red. And there's a big emphasis on Chinese characters symbolizing the Chinese zodiac animals. So right now we're in the year of the snake, but there's the dragon and the boar and the rat. A lot of times you'll see these characters in their paper cuttings. And something really cool about this is that these paper cuttings are included in the UNESCO Intangible Cultural Heritage List. So there's a lot of UNESCO sites that are protected across the world for their cultural value, for their historical value. But before this presentation, I didn't know that there's also an intangible list, and it's more like concepts and ideas that we're protecting. So here are 2 examples of those Chinese paper cuttings. The one on the left is one of those zodiac characters, the dog, and the one on the right is a little bit more elaborate, I guess, but it does have the boar on there as well. So you could see those themes throughout. If we go over to Japan, a lot of people are familiar with origami, the art of folding paper that originated in Japan and has been brought all over the world. But there's also a less known one called kirigami, which is origami plus the paper is cut. And it was developed after paper made its way from China to farther areas. And in the US, people started being more interested in kirigami in 1962 with the publication of a book by Florence Temko. And so when we're talking kirigami, we're talking something like this example here. It's one sheet of paper, but because of those folds, those cuts, you can make a 3-dimensional shape. This paper cutting art spread even farther, and it appeared in Europe after the 13th century. It was mostly introduced through Jewish culture, and it became a common Jewish art in the Middle Ages. It was connected with a lot of customs and ceremonies, especially associated with holidays, family life. And so these paper cuttings a lot of times decorated marriage contracts. They had different colors to them. And I came across this really interesting account, The Fight of the Pen and the Scissors, by a 14th century rabbi. And he described how he started cutting letters into paper because the winter was so cold that his ink froze. And so that was his backup plan, and might be one of the ways that this art form originated in the Jewish culture. And as paper became cheaper in the 19th century, this paper cutting became more of a folk art. It became more accessible to people, and there were a lot more people participating in it. And it kept spreading throughout the world. And originating in other places as well. So you've probably seen papel picado. It's a Mexican paper cutting. A lot of times they'll use tissue paper, and it's also very colorful, and they'll use it to decorate along the ceilings and doorways for a lot of different festivals and celebrations. And one that is near and dear to my heart is Slavic paper cutting. So I'm Polish, and I grew up knowing about what we call wycinanki in Poland. But there's also Ukrainian and Belarusian versions of this. So for these, you would cut out different shapes, a lot of floral themes. There's a lot of roosters, and you'll cut out different layers out of different colored paper and then glue them on top of each other. So here you have a white backing, there's a cutout black kind of pattern, and on top of that, they started layering reds and oranges and yellows, and gluing them down to make these beautiful, beautiful designs. So a lot of different cultures use paper cutting as a craft and a tradition. And I started cutting out snowflakes. I remember doing it like in grade school, but then didn't do it for a while. And then I was very, very bored and started cutting out snowflakes when I worked at Mammoth Cave. The wintertime didn't see many visitors, and we were required to be at the front desk. And sometimes you wouldn't see a visitor for the whole hour you were up there. And so I started playing around with scrap pieces of paper and sometimes cutting shapes into them. And people were like amazed. And I was like, wait, you didn't learn how to cut out snowflakes in grade school? And some people didn't have a recollection of doing that. I taught one of my supervisors how to cut out snowflakes. And then it turned into this whole big thing where this was back in the days of all the plexiglass. So I would put snowflakes up on the plexiglass. I started cutting cave related shapes, so like bats and flashlights into these snowflakes. Ended up creating a scavenger hunt to entertain my coworkers when there was nobody visiting the visitor center. And so I've decided to keep learning about snowflakes and sharing this with other people. So there's a lot of good resources out there if you've never cut out a snowflake or you don't know where to start. If you Google like snowflake template, a lot of times I'll throw animal in there. So like animal snowflake template, there's a lot that you can just print out. They'll give you instructions. And December 27th is Make Cutout Snowflakes Day. So we missed it by a little bit, but we can always practice for next year. There's a few different links that I've posted here, and TJ will put in the chat for everybody of ones that I really liked. They have like scientist figures in some of these. I've seen like Star Wars snowflakes. Some just have pretty shapes. The fisheries one has some sea creatures. And then the History Museum had some pretty good ones as well. So a few different options if you're looking to start at home. But as I'm cutting out snowflakes, sometimes I just make random shapes. I cut out all sorts of polygons and see what comes out. There's a lot of trial and error. A lot of these end up in the recycling bin. Sometimes I decide to get a little bit more creative and I start cutting animal shapes into them. So here I was trying to achieve a great blue heron, some swans, blue goose, the symbol of the National Wildlife Refuge System, and owls. And these would be kind of in the negative space or the cutout space where you don't really see them until you put them against a black background or a dark background. But you can also cut these shapes into the actual paper in the positive space. So here's some butterflies. And then on the bottom there's hummingbirds. They're kind of touching beaks if you look at that snowflake. So lots of options to play around, and I'm gonna walk you through it. So if you have any questions, I'll take questions as I rearrange my camera here, and we'll make some snowflakes. So prepare your papers and pencils and scissors as well.
And these were amazing, just amazing. Yeah. And I've seen them in person, Basia, the ones that you had at the visitor center. I'm
Yeah,
seeing yeah.
if you all come to the visitor center, on the bulletin board right now are a bunch of my snowflakes, so you can see how many animals you can find.
And feel free to add any questions you have, any comments. I think Basha is just getting her camera arranged, so she'll show us how to cut out one. All right, we can see your table.
Amazing.
Yeah.
So I had this fancy camera I tried to plug into my computer, and then the computer didn't want to work with it. So I have duct taped my regular camera to the top of my desk, and we'll see if we can make it work. All right, I'm not seeing any questions.
No
I'll just
questions so
quickly show
far.
you the Snowflake Bentley book. So this is about William Snowflake Bentley, that first person to photograph snowflakes. It's a children's book, so you can check it out from the library to learn a little bit more about his life and that process that he used. But in order to get started with snowflakes, I usually start with a square piece of paper, and there's a cheating way to do it, which is how I learned how to do it, where I make an eight-sided snowflake. And for that, you fold it in half again, and in half again. But as we learned, snowflakes are six-sided, and so we're going to have to do it a little bit differently. You can either fold your paper in half just like that, or you can go corner to corner like that. So just start out with a half fold any way that you like. And after you have that half fold is when it gets a little bit tricky, because we're trying to achieve six-sided snowflakes. We are going to have to fold this into thirds. So a lot of times I will kind of try to figure out what those thirds look like, but I end up with a very folded and unfolded and refolded piece of paper. So if you figure out what those angles are, you can also make yourself a little, not a cheat sheet, but I guess a cheat triangle, where if you've got those angles figured out, cut out a triangle out of cardboard, and then you won't ever have to guess on those angles again. And when you fold it, you'll have that beautiful shape with the thirds precisely correct. But if you don't have that cheat sheet shape, you're folding one side of your paper in and then the other side in, and you want these edges to align.
And you took a square paper, right? It was a
A
square
square
paper.
paper,
Perfect. Yeah.
I usually take an 8.5 by 11 sheet and just chop it so it's 8.5 by 8.5.
Yeah. Okay.
So if you were to unfold this, you can see we're getting that six-sided shape. We've got 3 and 3. So we are well on our way to making a snowflake, but in order to make those nice symmetrical shapes, we're going to fold it in half one more time. So the pattern for a six-sided snowflake, you're going to go half, then thirds, and then half again. And this shape right here will be your basis. The only thing you have to be careful of is when you folded it in, there's some excess right here. So if you cut anything above where the lowest paper is, that is not going to appear across your snowflake. So a lot of times, in order to prevent that, I will find that lowest place and I'll just cut off the excess. And I know everything below here will appear symmetrically. All of this one only has 4 layers instead of all the layers. So anything I cut into this will not be replicated 6 times. And once you have this is where you can start playing around. So a lot of times I'll just cut triangles, I'll cut crescents, and then I'll unfold it, see what it looks like. If I like it, I keep going. If I don't like it, I'll stop. And if you want to get more advanced, we're going to go back to that symmetry. So there's things that have bilateral symmetry, like for example, here I have a wolf or a fox. If I draw that line down the middle, it will be a mirror image on either side. And so these kinds of things help me kind of picture that. For example, if I take a swan and I fold it in half, it will not look the same on both sides. So that is not a shape that has that bilateral symmetry. But this kind of reminds me of cutting out Valentine's Day hearts, right? You fold the paper in half, you cut out half a heart, you unfold it, you'll get that full heart. So there's different shapes that you can do this with. An owl is another good one that has that bilateral symmetry. If you want to get even more advanced and fancy, you can do something like a deer. Another simple shape, a butterfly or a snowman, will have that bilateral symmetry. And a good place to start is by taking a pencil and drawing half the shape that you want. So say I'm wanting snowflakes with snowmen. I can picture a whole snowman. I would have to picture a half snowman, and I will take my pencil and draw out that half snowman. And then let's put just that right there. And I will cut it out and see if I get full snowmen.
And we all will be receiving a recording of this because I know I'll have to watch it a couple of times to fold that paper, but it's awesome. It looks very, very cool.
So I drew my snowmen, I cut them out, I added a little triangle here. And then when I unfold it,
Really nice. Wow.
I have 6 snowmen, and because of that bilateral symmetry, they're full snowmen now.
Yeah. And those six.
So
Yeah.
I said I like that design, but I want it to be fancier. So I will go back, and fold it back up the way it was before. And then I'll add some other shapes like diamonds. And it definitely helps if you have a nice pair of scissors. I have struggled through with some old dull scissors, and it's not as enjoyable.
Wow. It
Oh,
just
yeah.
transformed. Wow. Yeah.
Add in some more shapes, and there's your snowflake. But if you're feeling overwhelmed by the folding, you can start with a new sheet of paper and just do halves, and you will end up with an 8-sided snowflake. And if they haven't been to this presentation, they won't know.
Yes. Yeah.
So half, half, and then half again. And with this 8-sided fold, you don't have to worry about
Excess.
cutting off that excess because it's all going to be very symmetrical. If you fold it again though, you have to remember that this will only appear on half the snowflake. So you can also cut it off there. Any questions, feel free to put them in the chat or unmute yourself. Or you all can come to my in-person program on February 8th and get one-on-one guidance.
Yeah, that reminds me. Let me put the calendar of our events because I know that would be a good one to have. I'll post a link here. What's the most complex one have you ever built, Basia, and how long did it take you?
Oh, that's a good question. A lot of mine end up in the recycling bin.
Oh no, they end up on a wall. They're good. Yeah.
Most complex. There's a lot that I've made that are just very similar to the inside of this one. A lot of diamonds, little squares, things like that. And the more cuts you make, the more detail it'll have. So there's a lot of cutting something, unfolding it, deciding what I want to add to it, and then refolding it and adding those things. But I think the one I'm most proud of since I came here is my Blue Goose one.
Which one? Sorry. Oh, the blue
The
goose, right?
blue goose.
Blue
Yep.
goose. Wow. Yeah, nice. And now those Chinese, I mean, you said they made this kind of popular, and the paper that they had, the red paper, was that like some sort of colored paper they use, some specific type of paper, or
That's a good question. I'm not sure.
okay,
I'm not sure where the dye came from or how thick the paper was. I would have to look more into that.
yeah. But you've been using just the regular printer paper, right, to build this,
Regular
or
printer paper. Yep.
yeah. One of our friends, she is really, really artistic. I don't know she knows about it. I'll send her this link. So 'cause she also is similarly creative, and
Mhm.
I'll share this with her. I shared the event, but she didn't. Something must have come up. She didn't join.
Mhm.
This she loves to do this with her grandkids and all. So I think she'll really love this.
It's a great activity for fine motor skills for
I think
kids.
kids, yeah,
And a good way to talk about symmetry, throw some math in there.
yeah,
So for this one, I started out with that owl bisected.
yeah.
Hold it a little higher. Basically, I took half an owl, and hopefully when I open it up, I will have a bunch of whole owls.
They look like it. The great horn.
Yeah.
Yeah, looks really cool. All some activity for you when you're waiting for birds somewhere. Take a piece of paper and scissors.
So this one, because I folded it halves
Oh,
instead of the thirds, this one has 8 owls,
it also, yeah.
but this was the one with the 6 sides. So we've got a few more minutes. I'll go through that 6-sided fold again because it's a little bit confusing.
Yeah.
So you want to do half first. You can either go this way or corner to corner. I'm going to go half like this.
Okay.
And now I'm going to try for thirds. So that looks like about a third.
And you have the open side up, right? The
Mhm.
fold. Yes. Yeah. Okay. Yeah. I see
Yep,
it. Yeah. Good. I'm just trying to copy you. Yeah.
half.
Perfect.
Then estimate your thirds, and you want this crease to align with your fold. And then when you fold it over, this one should align with this. So sometimes I'll fold it like this, and then I
Mhm.
try to fold this one, and it goes too far over, which means I need to figure out my thirds a little bit better. But once you have the half and the thirds, this means it has 6 sides, and you fold it in half one more time to create that symmetry on each of those 6 sides.
Close enough.
Looks good. Yeah, lots of trial and error. So half, thirds, half. You can cut off any excess if you want to make sure you're not risking cutting something that won't appear across the whole design. And then you can play around
Yeah.
with it. And sometimes once you have it cut out, if you want to keep one, I'll lay it like between two books to flatten it out because there's a lot of folding.
Hmm.
They don't tend to stay flat.
Looks amazing, yeah.
Any questions, or I just overwhelmed everybody with all the math and science? There's a lot of things I saw when researching this that I haven't seen since like high school chemistry.
I don't see any questions, but it was really eye-opening, like some of the things, basic things, and you explained them very well, in very simple terms. Your presentation was just amazing. And the skill to watch at the end is like an artist at work, you're watching somebody sculpt something out. It's very
Well, I
good.
appreciate it, TJ. And if anybody is in the visitor center and sees me at the front desk, I also take requests. I see moose and squirrel snowflake from
Yeah,
Paul.
yeah.
I
Paul,
will take requests back to
yeah,
you.
will do. Yeah, no, thank you. Any other questions before we close for tonight? No, I don't see any. Basia, thank you again for your time. I know you had to go back to the office, but this one was amazing. Like continue this art, share it as much as you can. Definitely a very simple thing. A lot of people will enjoy.
Awesome. Well, I appreciate the opportunity to share this with you all.
Yeah. Thank you so much. Have a good evening, everyone. Bye.